Welcome to a new video and the final video in block 1 of TBMT42 that deals with the introduction of different model formalisms. And in this video, we will go through a variety of different models, but in much less detail. So here we will not learn how to formulate them. We'll just learn the very basics of what type of models they are, and maybe a little bit of what type of software you can use to run them. So we will talk about biomechanical models and Boolean models. I won't really talk about more than to say that they can be of the same character that we see now. So for instance, these reactions, but instead of having continuous variables of concentrations, you simplify it so that you either have 1 or 0. So it's like the simplest possible representation of a model. We'll talk a little bit about brain models, metabolic flux analysis models, MFA models, stochastic models of different kinds, and nonlinear mixed effect models that we'll come back to during the entire block 3. So it's a sort of axe block of some of the model formalisms that we don't have time to cover in depth in this version of the course, but that you at least should have heard of, so that you know you can say at least a few sentences about what type of models they are. Okay, so there's more to brain models and models describing the head than we have we have seen in the Hodgkin-Huxley example. So if you take it from the top level, this here I showed you a video in the live lecture. This is an example of a simulation with a model from the commercial application developed by Soul Machines, which already is a commercial product. It's used to dispense information at airports, for instance. And the language part is similar to this ChatGPT and OpenGPT and so on. So you can talk to it and you can interact with it. And some versions of this software also has a learning component, so it will learn to recognize you, and it will if you teach it things like teach it a word or something, it will learn it after a while. And on top of this, you can take away the skin and see the biomechanical muscles behind it. And if you're interested in this, there are some cool TED Talks and YouTube videos. Search either for Soul Machines or Mark Sager, who is one of the founders of this company. So in these models, they have machine learning type of models for the different brain areas that correspond to different functions, but they are not neuronal network models. So I want to mention those specifically. So here, each node in these type of models describe the electrophysiology of a neuron, of a nerve cell. And this is done using these Hodgkin-Huxley type of equations that we've gone through in the previous video. And here, I just want to add the fact that the sort of architecture that you see here in terms of different layers, those correspond to the actual anatomy of different areas of the brain. So this is, for instance, the different layers of the cortex, which is fairly well characterized. So they sort of represent that. And these type of models are typically not formulated by hand because the models are very, very big, tens of thousands or hundreds of thousands of equations easily. But the basic equation, the equation for for each cell here are similar to the ones that you have seen in the Hodgkin and Huxley video. And apart from that, in the brain, you can simulate other things. You can simulate biomechanical properties of the propagation of sound waves if you want to simulate the hearing mechanism and all of the biomechanical properties that has to do with that. You can simulate using other types of models, other physical properties like the electromagnetic waves that are involved in either this deep brain stimulation, where you have an implant that you use to treat Parkinson, or a new type of external electromagnetic stimulation. So there are different researchers at LEO that are working with these different types of models. So moving now to other parts of the body and almost the body as a whole, but from a biomechanical movement point of view. Here we see a simulation of movements. This is me with digital twin of myself with clothes, and this is just a skeletal muscle version of me. And this is simulated in a software where the models are simplified. So here you see the muscles, but the basis of this is just to define which joints can you actually turn, which degrees of flexibility do you have. And then in each node here, you have a separate little system. So you define the joints, and then they are interconnected in this way. And the local equation, the local coordinates here are classical Newton's laws, but they are typically formulated in a fairly advanced way, more advanced than you learn in high school. So usually using Jacobians and Hamiltonians and that type of things. And again, here you don't really look at the equations yourself. You formulate it in this way, where you sort of define what the degrees of freedom are, and then the actual equations are automatically generated in, for instance, a software called OpenSea. And these type of models can also be used. So the movements here are actually not simulated, but recorded and then translated to the model. So they are recorded using motion capture, the same that you use in special effects in movies. So when you record Gollum, for instance, there is a character that is moving around, and then you can capture those movements and you can translate it to these type of skeletal movements to calculate biomechanical properties like forces and torques and that type of stuff. Okay, so yet another model formalism is NLME, nonlinear mixed effects models. And here you want to describe the dynamics of individuals. So you have the states for an individual I here, and you have the input, and you have the parameters, which we here call phi. And this is just as usual. And the new thing here in these nonlinear mixed effects models is that you also describe at the same time the population. So you also have for these phi's an equation, which says what are the typical values on the population level, what are the unique modifiers to that population value. So these are called the random effects. These typical values are called the fixed effects. And it's because you have both of those that you call it mixed effect. And then you also have covariates, which talk about basically the correlation, you could say, between these different parameters. So we will spend the entire week 3 to understanding these type of models, because they are very important when you, for instance, fit to patient-specific data like drug development data. So, finally, let's look at a few more. So stochastic differential equations. We will talk a little bit about this so we'll talk about all of these when we talk about simulation as well. So you sort of have a very basic understanding on how to do this. So a stochastic differential equation is just as before. You have a state, dx, but you have multiplied up here the dt. So we have the parameters and the input, but you don't have the x dt, but you have dx equals, and then you have the dt up here. And that's because a stochastic differential equation like this, where you have a Wiener process, which has a new random number each time you ask it for a number. This is not continuous, so you can't do continuous. You can't talk about the derivative. You can only talk about the dx with respect to dt. So the derivative is simply not defined. So in these type of stochastic processes, you have to do a more algorithmic approach to the analysis, or a more theoretical approach. And this brings us, and then you have sort of a function here which also describes how this noise comes into the picture. So this brings us to another type of stochastic and more algorithmic approach, which is to use Monte Carlo simulations. So here we see an animation of photon scattering in tissue. So this is the expertise of Thomas Strömberg, who is the head of department, and some of you might have had in some courses. And some of you might even have learned about these type of models, which basically describes a series of steps where you move the photon and you have a scattering step, and then you have some stochastic decisions here, which means that you simulate many times individual photons that each time does something new, because it's the stochastic process. And it's not the differential equations, it's sort of a series of development of the state, you could say, where you also allow for this type of stochastic properties. So we will come back to Monte Carlo processes when we talk about uncertainty estimation in the parameter space. So then it will be a little bit more clear what these type of models are. So final example is elementary metabolic unit or metabolic flux analysis models. So metabolic flux analysis, they do what the name suggests. They try to determine the flux of metabolic reactions. So here we have some metabolite A, which is converted to B and D and F and so on. And what you want to determine here is how quickly each reaction flows. And in this type of elementary metabolic unit models, which is specific formalism, which is developed to deal with tracer-based data. And the tracer here is that you have replaced some of the carbon atoms in these metabolites with carbon-13, so that you then can use mass spectrometry data to get mass isotoper distributions, which basically says the distribution of how many, what percentage of each metabolite has how many carbon-13 atoms. So this is the percentage that has 0 carbon-13 atom. This is the one that has 1 carbon-13 atom, and so on. And these type of models that are dedicated to do this particular type of analysis, they are called elementary metabolic unit models, or one way to analyze these type of models is to use EMU models. And this is usually a static type of model. So you see there are no derivatives here. So you have simplified the analysis to only describe the steady state. So you don't describe the kinetics. Yes. So if you want to read more about this, here is a paper that we published, and we hope to get into a cool journal with another paper fairly soon. Yes. So this was a little overview, by no means exhaustive. There are many other type of formalisms as well, but these are some of the ones that we have decided to include in the course that you should know, at least to say like a couple of sentences about each of these type of models. Okay, that was it for this final video on model formulation.